In the aftermath of a disaster, every second counts. Emergency managers need real-time intelligence to decide where to send aid, how to reroute rescue vehicles, and which roads are safe to travel. But processing aerial imagery from drones, small uncrewed aerial systems, or sUAS, is time-consuming, labor-intensive, and often delayed by poor connectivity. That's where artificial intelligence comes in. Today, we're diving into a groundbreaking new benchmark dataset, CRASAR-U-DROIDs, the largest known dataset for road damage assessment using post-disaster sUAS imagery. This dataset isn't just big, it's transformative. We're talking 657.25 kilometers of labeled roads, spanning 10 federally declared disasters, from hurricanes to earthquakes, captured at resolutions as fine as 1.93 centimeters per pixel. That's high enough to see individual debris piles, flooded lanes, and even cracked asphalt. But this dataset goes beyond scale. It solves three critical problems that have plagued the field for years. First, prior datasets were too small. Most were limited to a few square kilometers, making it impossible to train robust, generalizable models. Second, many relied on low-resolution satellite imagery, which simply can't capture the fine details emergency managers need. A tree branch on a road, invisible from space, but from a drone flying 50 meters above. Clear. And third, no prior dataset had been operationally validated. Models were trained and tested in labs, but never deployed in real disaster response. This work changes that. The team at Texas A&M's CRASAR lab, led by Thomas Manzini, Priyankari Parali, Raisa Karnik, and Robin Murphy, didn't just build a dataset. They built a practitioner-driven system. They consulted with the Federal Emergency Management Agency, FEMA, the Texas Department of Transportation, and local emergency responders to design a 10-class road damage schema that matches real-world decision-making. Let's break it down. Each road segment is labeled as one of 10 conditions. Clear road, fully passable, no obstructions. Partial flooding, standing water covering part of the road. Total flooding, completely submerged. Partial obstruction, debris, vehicles, or vegetation blocking part of the lane. Total obstruction, complete blockage. Partial road condition, moderate cracking, crumbling surface. Total destruction, road collapsed or gone. Partial particulate, sand, mud, or lahar covering part of the road. Total particulate, completely obscured. And not able to determine when visibility is too poor. This isn't just academic. It's operational. When a first responder sees total flooding, they know the road is impassable. When they see partial obstruction, they know a heavy vehicle might still pass, but not a fire truck. But here's where things get technical and critical. When you overlay a pre-existing road network, like OpenStreetMap, onto drone imagery, misalignment is common. Roads shift due to GPS drift, image stitching errors, or terrain distortion. In this dataset, 59 kilometers, about 9% of all roads, were misaligned from their actual physical location. And that's not just a data issue, it's a performance killer. The researchers tested 18 baseline models, ranging from classical UNet architectures to modern vision transformers, on both aligned and unaligned road lines. The result? When models were trained on misaligned data, performance dropped by an average of 5.6% in Macro IoU, a key metric for segmentation accuracy. One top-performing model saw its IoU drop from 0.331 to 0.312, a difference that could mean the difference between a correct and incorrect assessment of a critical route. Even more alarming, 8% of adverse conditions, 11 kilometers, were mislabeled because the model was evaluating the wrong physical location. That's not a small error. That's a real risk in disaster response. So how did they fix it? They introduced 9,184 spatial alignment adjustments, vertex-level corrections to reposition road lines so they match the actual road in the imagery. This wasn't just a one-time fix. It was a systematic, repeatable process using vector field transformations, proven in prior work, but now applied specifically to road lines. And the data format? Intentionally decoupled. Road lines are stored separately from the annotation polygons. Why? Because this allows future models to be robust to alignment variations. They can compute the intersection between the road line and the damage label, regardless of whether the line was shifted during capture. Now let's talk about the models. 18 baseline models were trained and evaluated. Each treated road damage assessment as a semantic segmentation task, predicting damage labels for every pixel along a road. The best performer? The UNet with attention, achieving a macro IoU of 0.331 on the aligned simple task, where models predict whether a road is no damage, partial, or total damage. But here's the twist. Even the best model still scored below 0.35. That's low for a modern deep learning system. Why? Because this problem is inherently noisy. The damage classes are subtle. Partial flooding might only cover a few pixels. A tree limb might obscure just a corner of the road. And with high-resolution imagery, models need massive receptive fields to capture context, something traditional CNNs struggle with. But vision transformers, they're promising. Models like ViT plus UpperNet and ViT plus Segmenter showed strong potential, especially when pretrained on large-scale geospatial data. Yet even they lagged behind. highlighting that contextual reasoning and long-range dependencies are key challenges. And then came the real test. During hurricanes Debbie and Helene in 2024, the Attention UNet was deployed operationally in Florida. It processed a 3-square-mile orthomosaic in just 5 minutes on a consumer-grade NVIDIA RTX 4090. Output was converted to KML files and shared with field teams. Feedback from practitioners was eye-opening. First, false positives were far more tolerable than false negatives. If a model said a road was blocked, responders would check it, because missing a real obstruction could be fatal. But if it labeled a clear road as damaged, they'd ignore it. The sheer volume of clear roads made that label meaningless in practice. Second, timing mattered. Early in a disaster, when information is scarce, even low-confidence predictions are valuable. Practitioners were willing to accept more errors if they got faster insights. So yes, the model isn't perfect, but it's operationally useful, and that's a game changer. This work isn't just about a dataset. It's about closing the gap between research and reality. It releases the largest sUAS road damage dataset ever, 657, 25 km of labeled roads. The first dataset to address spatial alignment errors, with 9,184 vertex-level adjustments. A practitioner-validated schema developed with federal agencies. 18 baseline models ready for immediate use in disaster response. And a clear warning: spatial misalignment is not a minor data issue. It's a systemic flaw that degrades model performance and risks real-world consequences. Future work will focus on expanding the dataset with more disasters and non-disaster imagery, improving model performance, especially on the full labeling task, and critically, evaluating the ethical implications of false negatives, missing a blocked road versus false positives, wasting resources on a clear one. This research is not just academic. It's a call to action for the machine learning, computer vision, and robotics communities. We must stop building models that only work in controlled environments. We must build systems that work in the chaos of real disasters, with noisy data, misaligned maps, and urgent decisions. Because when lives depend on it, accuracy isn't enough. Robustness, reliability, and real-world validation are essential. This is the future of disaster response. AI that doesn't just analyze data, but helps save lives. If you're working in AI for social good, remote sensing, or emergency response, this dataset is your starting point. It's open-sourced. The code is on GitHub. The data and models are on Hugging Face. And the message is clear: don't just train models. Deploy them. Test them. Improve them. Together. Because in the next disaster, the next road that needs to be cleared, it might be the one your model helps find.